An experimental study of the TiB2-Reinforced AA7075 manufactured by the Stirt casting technique. Abstract: metal matrix composites based on the Aluminium 7075 alloy are widely utilized in structural, aerospace, marine, and automotive applications due to their high strength, lightweight, and low manufacturing costs. In this study, an attempt was made to produce an Aluminium Matrix Composites, AMCs, using reinforced AA7075 with TiB2 and compared the characteristics of AMCs by using the Stirt casting method. AA7075/TiB2 specimens were made with varying weight percent, 3, 6, 9, and 12, of TiB2 particles. The results obtained by the experimental studies regarding mechanical properties indicate that increasing the weight percentage of TiB2 in the composition improves the mechanical characteristics such as tensile strength, hardness, impact strength, density, and porosity. A salt spray test was performed to examine the corrosion behavior of reinforced composites in relation to the parent material. Optical microscopy is used to examine the microstructure of reinforced composites with TiB2 for uniform particle distribution in the aluminium molten phase, and the results are also presented in this paper. The particles of TiB2 were characterized by their uniform distribution, strong connection, and excellent AA7075 bonding. The deposition of TiB2 particles improved the AMC's microhardness and ultimate tensile strength. Keywords: Stirt casting, metal matrix composites. Microstructure, mechanical properties. Introduction: conventional materials cannot meet the demand for new materials with unexpected combinations of features. Metal matrix composites, MMCs, have emerged as critical materials for structural, electrical, and thermal applications. Modern technologies demand not only strength but also lightweight and improved performance. They are preferred over monolithic commercial composites because they have a higher strength-to-weight ratio and cheaper manufacturing costs. Due to their higher strength, high elastic modulus, and increased wear resistance over conventional base alloys, reinforced MMCs-based aluminium alloys have matured into high-performance materials for the aerospace, chemical, automotive, and transportation industries. For this wide range of outstanding features of metal matrix composite with TiB2 reinforcement, many researchers studied and experimented with the mechanical characteristics of aluminium alloy with TiB2 reinforced matrix composites. AA7075 materials have been widely employed in recent decades to manufacture desirable aerospace and marine applications, turbine casings, missile tail cones, bicycle components, and automotive engine casings, among other things. 1,2. In particular, AMCs had high strength and increased fatigue and wear resistance. 3. Recent research interests include the AMC's ability to alter physical, mechanical, and tribological properties, etc., by changing the phase of the component or filler material. 4. The mechanical properties have been significantly improved by adding different weight percent of reinforcing ceramic particles in aluminium alloys. The addition of TiB2, SiC, Al2O3, BaCl2 and reinforced particulates in aluminium increases tensile strength, compressive strength, yield strength, hardness, and bending strength, while ductility decreases 5 to 9. TiB2 is a potential choice for AMCs among numerous ceramic reinforcements, due to its multiple desired features. TiB2 is a resistant compound that has outstanding qualities such as a high thermal conductivity, strong hardness, and good modular properties. At the reinforcing and matrix contact, TiB2 does not react with aluminium to generate a reaction product. 10. Some investigations of aluminium AMCs reveal a reduction in the friction coefficient and an increase in the weight of percent of graphite particles. 11. The presence of TiB2 particulates in aluminium alloy improves the dimensional stability while conducting thermal cycling tests. 12. The AA7075/TiB2 AMCs were manufactured and the hardness, tensile strength, and yield over the matrix were improved. 13. Aluminium provides increased strength, flexibility, high temperature, and electric conductivity, but poor stiffness, whereas carbide and fly ash are stronger, stiffer and more resistant to good high temperatures 14, 15. All processing processes are divided into two groups, solid-state processing and liquid-state processing. Every method has a limit on AMCs with particular matrix alloy and ceramic particle combinations. Therefore, much focus is put on research in the development of processing techniques for the production of AMCs. Due to its simplicity, ease of modification and application for huge volumes, the liquid processing method is beneficial. The liquid processing approach either includes introducing ceramic particles to the molten metal outside or manufacturing them in the melt. The target underlying the development of aluminium and titanium diboride metal matrix composites to enhance the mechanical properties. Numerous strategies of production of metal-based composites are powder metallurgy, spray deposition, liquid metal infiltration, compression casting, and agitation casting 16 to 20. Despite the availability of numerous processes, the Stirt casting technique is used in large-scale commercial manufacturing of reinforced AMCs. This approach is used in this study because of its simplicity. The significant impacts of this paper are given as follows. Fabricated AA7075/TiB2 metal matrix composites with varied TiB2 weight percentages using the Stirt casting or liquid state method. Examined the microstructure of the metal matrix composites for distributing the Aluminium 7075 alloy-based TiB2-Reinforced particles. Experimentally evaluated the mechanical characteristics of the MMCs and compared them to the base metal Al 7075 and achieved remarkable results. 2. Materials and methodology. In the present study, attempted to manufacture AMCs from commercial TiB2. The authors used AA7075 alloy as matrix material to manufacture the AA7075/TiB2 AMCs. Titanium diboride, TiB2, is purchased from M/S Innovative Growth Enterprises, Lutharan, Punjab, India. AA7075 is commercially available in the local market. Aluminium 7075 alloy. Aluminium 7075 is one in all the strongest aluminium alloys obtainable, and it's commonly used for structural components that are subjected to a lot of stress. Zinc is the major alloying element in aluminium 7075. It has a higher tensile strength than many steel products, as well as good fatigue strength and mock inability. It has a weaker corrosion resistance than many other aluminium alloys, yet it possesses great strength. In AA7075, copper presence makes it more prone to corrosion, but this is a necessary trade-off for such a strong yet workable alloy. Gears, shafts, aeroplane parts, valve parts, low-volume plastic mold tools, and blow molds for plastic bottles are all examples of applications. As a result, the material for this study was identified. The AA7075 chemical compositions is shown in Table 1. B. Titanium diboride, TiB2. At high temperatures, titanium diboride, TiB2, may be a hard ceramic metal with great strength, durability, and wear resistance. Its usage in armor sections is due to its high density along with high modulus of elasticity and compressive strength. Most chemical reagents have little effect on it, and it has exceptional wettability and stability in liquid metals like zinc and aluminium. Crucibles for molten metal, cutting tools, and wear-resistant coatings are also made from it. In terms of chemical stability, TiB2 is more stable against pure iron than tungsten carbide or silicon nitride. TiB2 resists oxidation in air, hydrochloric, and hydrofluoric acids at temperatures up to 1100 degrees Celsius, but reacts with alkalis, nitric acid, and sulfuric acid. The structure of TiB2 and units in hexagon layers are shown in Figure 1. The TiB2 chemical composition is given in Table 2. 3. Experimental methodology. Stirt casting and preparation of specimens. For the manufacture of AMCs specimens, the Stirt casting process, also known as liquid casting method, is used, in which a dispersed phase is mechanically mixed with molten metal. After that, the liquid composite material is cast using traditional casting techniques and treated with conventional metal forming technologies. AMCs were reinforced with TiB2 at a composition of 0, 3, 6, 9, and 12% by weight. AMCs were fabricated by using a stir casting process, also known as a liquid metallurgical technique. The required quantity of AA7075 was weighed on an electric scale, then filled in a crucible and placed inside the induction furnace. In 3 hours, the furnace temperature is increased to 800 degrees Celsius, AA7075 melts to a molten form at 800 degrees Celsius. Simultaneously, a mold for casting specimens is prepared. The interior surface of the mold is coated with graphite powder, which provides adhesion. The schematic diagram of stir casting process is illustrated in Fig 2. In the muffle furnace, TiB2 in the weight of AA7075 is preheated at 250 degrees Celsius at the same time. The purpose of preheating is to remove moisture from TiB2, to increase the reaction rate when mixed with the base metal. In the process of stir casting, stirring is performed at 400 rpm to form a vortex in the molten metal. When the vortex is formed, the preheated TiB2 is poured at a constant discharge into the base metal. After mixing, stirring is performed for 6 minutes. While stirring, an inert gas, argon, was continuously supplied, such that molten metal does not react with atmospheric air. The crucible containing molten AA7075 is taken out and poured into the mold cavity. It is then cooled at room temperature. Fig 2. Schematic diagram of stir casting method. Similarly, the same operations are performed for the remaining types of specimen composites. In AMCs manufacturing, preheated reinforcements are poured simultaneously into the vortex to get proper mixing and then poured into the mold and cooled at room temperature. The process of stir casting and preparation of mold process is shown in Fig 3. Fig 3. Stir casting and molding process. Microstructure study. The microstructures study was carried out for the samples prepared with different AA7075 compositions with different TiB2 percentages of reinforcements using metascope metallurgical microscope. Keller's reagent etchant is used to etch aluminium alloys to reveal their grain boundaries and orientations. The microstructural analysis is performed to ascertain uniform distribution of TiB2 reinforcement in AA7075 metal matrix. C. Mechanical properties observation. 1. Hardness. This test method covers the determination of the Rockwell-Brunel hardness of metallic materials, using load of 250 kgf, and the size of indenter diameter is 5 mm. The test method is carried out according to the test procedure IS 1500:2005-23. Brunel hardness number, HBW, is a number associated to the applied load and the surface area of the permanent impression. Taking the impression values and calculated the average as a final result of hardness in HBW 5 mm/250. Where F equals force in N. D equals diameter of the ball in mm. D equals mean diameter of the indentation equals D1 plus D2/2 in mm. 2. Tensile strength. The tensile strength test is performed in line with ASTME 824 using a computerized universal testing machine. The crossbeam speed is 5.0 mm per minute, and the sample rate is 9.103 pts per second. To calculate the final tensile strength, yield strength, and stretch percent, a typical tensile test specimen off-gauge length 36 mm is utilized. The specimen used for tensile strength is shown in Fig 4. Fig 4. Tensile strength test specimen, ASTME8. 3. Charpy impact test. The Charpy impact test, Fig 5, is used to determine the impact resistance of AA7075/TiB2 at room temperature, according to IS 1757, Part 1, 2014-25. The test piece dimensions are 55 mm x 10 mm x 10 mm in size and must be squarely against the supports, with the notch's plane of symmetry being within 0.5 mm of the striker's plane of swing. End stoppers are used to position the specimen test piece length to tolerances in order to achieve this. Fig. 5. Schematic of Charpy impact test 4. Density and porosity. The practical density values of the composite specimens have been obtained experimentally by using a density kit. The theoretical density values are calculated by applying the mixture rule in accordance with reinforcement weight %. The porosity of the reinforced composite is also calculated and the results are presented in the results and discussion section. Theoretical density equals density A * mass fraction of A plus density B * mass fraction of B. The porosity values are calculated using the values obtained by theoretical and practical densities as given below. Porosity equals theoretical density practical density / theoretical density *105. Salt spray, fog, test. In the present work, a salt spray test has been performed in accordance with ASTM B11726, in which the specimens are exposed in a closed chamber at 95 of 35 OC, to fog emanating from a 5% sodium chloride, NaCl, solution. Rubber wires are used to hang specimens inside the test chamber so that they are sprayed evenly on all sides. The salt spray tests were conducted at M/S Hyderabad Engineering Lab, M/S Hell, Hyderabad. All test specimens are placed for 5 hours in a salt spray chamber before being removed, cleaned with distilled water, and inspected by counting pits. For results and discussion saw. Microstructure analysis. Figures 6a to 6d shows the representative microstructures for varied weight % composition of TiB2, i.e., 3%, 6%, 9%, 12%, reinforced with AA7075 AMCs produced by Stirt casting method. When particulates are introduced externally, a number of variables, including pore weight, pore agitation, and density difference between matrix alloy and TiB2 particles, lead to cluster formation. Further, when particles are introduced externally, local melt temperature lowers. The connection between particles is weak in clusters, resulting in low mechanical characteristics. However, the reaction shows excellent bonding in particles in clusters produced by the Stirt casting approach. Fig. 6. Microstructure of A. A7075 plus 3% of TiB2, B. A7075 plus 6% of TiB2, C. A7075 plus 9% of TiB2, D. A7075 plus 12% of TiB2. The microstructure of the composites exposed that TiB2 particles are scattered equally and uniform particles are existing in the metal matrix. This indicated that Stirt casting process used for the manufacture of the specimens are satisfactory. Furthermore, the microstructure of A7075/TiB2 made by Stirt casting indicated a strong bond between the matrix alloy and the reinforcement particles. B. Mechanical properties. The mechanical properties including hardness, tensile strength, percentage elongation, impact strength, density, porosity, and corrosion test results of A7075/TiB2 specimens are examined experimentally for this study. 1. Hardness. The Rockwell-Cumbrunel hardness tester has been used to test the hardness of all test samples using a ball indenter, and the hardness results were recorded. In Figure 7, the hardness number, HBW, is plotted for varied percentage of TiB2 composites. The mechanical hardness of the A7075 is improved the inclusion of weight % of TiB2. Fig. 7. Comparison of hardness with weight % of TiB2. The test results depicted that, the hardness is enhanced with the increase of weight % of TiB2 in A7075. This is owing to the increased surface area of the matrix and the smaller grain size of TiB2 particles, which are harder than A7075 particles. The presence of hard TiB2 particles controls the deformation of the hardness tester during indentation. 2. Tensile Test. A computerized universal testing machine is used to test the ultimate tensile strength and percentage of elongation. Figure 8 depicts that the tensile strength and percentage of elongation output of the test results for varied weight % of TiB2. From the test results, the tensile strength is improved and the elongation percent is reduced compared to the basic material with the addition of TiB2 particulates. The tensile strength of the base material to AMCs increased from 80.17 N/mm2 to 199.8 N/mm2 respectively. Subsequently, percent of elongation of the base material to AMCs also decreased from 2.6 to 1.2 respectively. The incorporation of increased weight percent of TiB2 with the basic material produces the best results in comparison with the AA7075. The tensile test specimens are also shown in the figure 8. Fig 8. Tensile strength with variation percent of TiB2. The displacements obtained when ultimate load acting on different samples varied weight percent of TiB2 reinforced with AA7075 is shown as tensile load vs displacement curves, Fig 9. Fig 9. Tensile load vs displacement graph. The Stirt casting technique results in defect-free TiB2 particles that maintain their integrity under tensile loading. The TiB2 particle refines aluminium grains, providing more surface area to withstand the stress. The transparent and excellent bonding interfaces delay particle separation from the aluminium matrix. Thus, TiB2 particles increase the AMC's hardness and tensile strength. The higher the TiB2 weight percent, the more the above-mentioned variables affect the mechanical characteristics. When the TiB2 weight percent is increased, the percent of elongation of the AMCs will drops. Similar results have been verified in the literature. Survey 18,19. 3. Impact test. The impact tests are performed on the test specimens with a notch depth of 2 mm and a notch angle of 45° is considered. The impact values obtained for AA7075 and TiB2 composites are shown in Figure 10 for the test samples. From the Figure 10, it can be observed that, the impact strength of 16.67% increased on addition of weight percent of TiB2 with base material. Fig 10. Comparison of impact strength of various percent of TiB2. For density test and porosity, theoretical densities are calculated for the composite specimens by using formulas, and practical density tests are also performed on all the samples by using density kit to find out practical density values. These density values are plotted and compared in Figure 11. It can be seen that, TiB2 reinforced composite densities are higher than the AA7075 base metal due to increasing the mass properties of composites. Higher weight percent of TiB2 exhibited to the higher density, and the matrix composites are sufficient strength to support secondary processing like sintering, machining, or extrusion, etc. The porosity results of the samples are computed and plotted as shown in Figure 12. In general, the porosity due to the increasing the weight percent of TiB2 exhibited a downward trend except for the composites reinforced with weight 3% of TiB2. 6. Salt spray, fog. Test. The samples were inspected for rust particles and pitting marks after conducting 5 hours of salt spray test in a closed chamber. The corrosion was indicated after 5 hours in the case of bare material AA7075, whereas the corrosion was not generated in the case of AA7075/TiB2 reinforced composites. All the test specimens are in good condition and found free from corrosion. Consequently, it is not necessity to further corrosion test for the test specimens. Conclusions from the results obtained for AA7075/TiB2 AMCs. The mechanical properties increased with the addition of weight percent of TiB2 reinforcements to the base metal. Through microstructure study, a fairly uniform distribution of materials is observed. The ultimate tensile strength is increased from 80.171 N/mm2 to 199.80 N/mm2 by varying the weight percent of TiB2 particulates to the base material. The AMCs have a higher hardness value than the base alloy by increasing the weight percent of TiB2. It is observed that the increasing hardness from 97.93 HBW to 106.73 HBW of AMCs, and that the reinforced composites with a higher hardness results have better wear resistance. The results of the impact test for AMCs increased from 21 joules of the base material to 25.1 joules of TiB2 reinforced composites. The density of the reinforced alloy is greater than the A7075 base alloy due to the addition of hard TiB2 reinforcement particulates having a higher density into the alloy matrix. Due to this reason, the composite with TiB2 as the reinforcement material will have a high porosity value. Finally, the composition of A7075/TiB2 has good corrosion resistance within the specified time compared to the base material, and also it is suitable to industrial applications. Acknowledgement: the authors wish to acknowledge M/S Hyderabad Engineers Laboratory, Hyderabad, for providing laboratory facilities and colleagues who have directly or indirectly contributed information to this paper and suggestions on the present work.